All right, so
Yeah, I mean, are you also going to do the record for the Saturday's lecture?
I'm going to, yeah, I will record Saturday also. Why not?
Okay, thank you very much.
So this way, if you are not there, you can, yeah. Remember, that is just a review class, okay?
Professor, your microphone doesn't sound so good. Are you a little close, maybe?
Doesn't sound good. I thought somebody said it sounds good. How about now?
No, Professor, it's not clear.
Not clear?
Yes, Professor, it sounds a bit hazy. It's like the microphone is too close, probably.
Too close?
Yes, Professor.
I mean, I can, okay, so I'll, this is all, anyway, let me speak for a few minutes. And how about now? Can you hear me well?
Yes, Professor.
Better.
Yeah, okay, so I don't have to get too close to it. That's good. So before we start, Saturday I put an extra session. Mostly it will be on matrix algebra, just to review, and then you should also read up. But we'll review something, things on positive definite matrix. So I'm going to continue with the stochastic processes. Sushant, how many? 40, 50?
44.
We are missing 10 people. All right, so students, remember, just to let you know, I'll stop the lecture around 5:15. So like last time, you will get a exam in the mail. Solve your problem, because your problem is may not be the same as your friend's problem. So don't try to fool around. And moreover, you should, like last time, all of you should keep the video feed on. If you don't see the video feed, I'm going to make a note, and I will simply mark 0. So you need to keep the video feed, unless you have a good reason not to put it up. And so one way these tests are actually exams, because whatever is happening here, I'm going to take I think I told you, I'm going to take the mini test 1, 2, 3, average it out. That will be your midterm, 35 points. Then the next 4 or 5 mini test will be your final exam, about 45 points. So each of these mini tests are about 10 points out of 100. So if you miss them, you get a 0. If you make mistakes, you get 0. I mean, you lose points. So I'm giving you a lot of time, and we are only dealing with one problem at a time. And remember, the solutions are there. So those of you who scored poorly, please look at my solution. And if you have, if there is an issue with the grading, I'll look at it. But I want you to look at it first, and then only I will look at it. And many of you have done very well. So I hope I already gave you a hint about what is going to happen today. So I hope you have come prepared. But let me go on with the session. What is it, Sushant? 50?
$46.
Okay, very good. So that's good. So are you able to hear me now?
Yes,
Yes,
Professor.
Professor.
Okay, very good. So look at here. I wrote, just to start with, this is what we were discussing last time. Strict and stationary processes and wide and stationary processes. So as I said, a stochastic process is a collection of waveforms. On the x-axis is time. On the y-axis is possible realization, psi. So it's a function of 2 variables, t and psi. Generally, we write it as x of t. So psi is the random part. Stochastic or random part comes from here. So depending on the value of this, you will get a different realization. So if you fix a time, you see multiple values at a fixed time. So that behaves like a random variable. So you have a random variable here, you have another random variable at T2. So question is, what is their joint behavior? So the joint behavior is through joint density function. If you take any number of time instance T1, T2, Tn, you have their joint density function. So if you simply shift in time all of those by the same amount C, you'll get a new set of random variables. Instead of x1 through xn, x1 prime through xn prime. And they have their own joint density function. If these joint density functions are the same, then we call the process to be stationary. This should be true for any n and any C. Remember, n is the number of time instances we decided to choose, x1 through t1 through tn. N is arbitrary here. Similarly, C is the time by which we are shifting. So irrespective of the values of n and C, if this holds, then we call the process to be strict and stationary. We saw two consequences of strict and stationary. I'm not going to go over everything now. One was the mean of the process is constant, and the autocorrelation depends on T1 minus T2. So if we use those two properties, the mean of the process is constant, and the autocorrelation depends on T1 minus T2. And if you only worry about these two properties, remember, nothing to do with density function here. Density function is here. If you deal with these two, then we call it to be a Whiteson stationary processes. So we saw, so one of your homeworks is, for example, so we saw several examples. X of t is Poisson with parameter lambda t. If expected value of x of t is then lambda t. Remember, Poisson process means things arrive randomly. The arrival instance t1, t2, etc. are random, such that if you take a time slot, any time slot, the number of arrivals there follows a Poisson distribution with parameter proportional to whatever is the length of this time slot, lambda t. So expected value of x of t is lambda t. And last time I showed you that t1, this is going to be, what was it, lambda squared t1, t2 plus lambda minimum of t1 comma t2. So you can see this is not a Whiteson stationary process, not Whiteson stationary. And similarly, we also looked at another example, which was Wiener process or random walk. You do small random walks, and then you add them up and take the limit as n goes to 0. Right? That was the Wiener process. And we saw that also because of a large number, this is a Gaussian process. Remember, a large number of random variables are added here. And we went through it. Each of this is, let's say, probability of xi equal to plus 1 is 1, I mean half. Probability of xi equal to minus 1 is half. So this is like a Bernoulli random variable, head or tail with equal probability. So the mean is 0, each one of them. And we saw that the autocorrelation function, we did this last time. I'm not going to go through this again. Expected, anybody remembers what it was? Expected value of W1, W22? Anyone? Alpha times minimum of T1 comma T2. Remember, this was Saturday. I'll go. Or if you have seen the videos, there are other ways you can prove that this is an autocorrelation function. So minimum is an autocorrelation, maximum is not. So you need to prove it why it is not. So here is an example of a not stationary process, right? Non-stationary. So remember W of t. So I'll scan this and send it to you later. So W of t is a Gaussian process with zero mean and autocorrelation function equal to alpha minimum of T1 comma T2. So clearly not stationary. Now, sometimes strange things can happen. Look at this process. So this is like a complex, this is of course a complex process. This is a real process, right? It's just random walk up or down. So what I am doing is I create this is a modulation. So if you take this to be cosine plus sine, this is like phase modulation, right? So what I am doing is phase modulation of a Wiener process. So let's see. So that's a new process. This one is a new process. So let's say it's a mean and autocorrelation function. So expected value of x of t. And here I'm going to assume that these two are independent. So what happens is if you modulate the Wiener process and transmit, by the time it comes to the receiver, there is a random phase. So you can assume it to be that way. And random phase is independent of the Wiener process. So anybody, what will be the expected value of this process? Anyone? So you can write it this way. What else can you say? These two are independent. So you have to use the probability concepts now. Anyone? WT and phi of t are independent. Anybody remembers anything? If x and y are independent, then what about gx, expected value of gx and hy? Hello?
Independent.
They are independent. Somebody send me something. I can't read it, but let me move on. So just illustrating that this is the results from probability. If x and y are independent random variables, and if you create a function of x and y separately, then these two are independent. If these two are independent, the expected value of two them are the product of the expected values. So what about the second term? That should be easy. This is like cos phi plus expected value of cos phi plus j expected value of sin phi. If phi is uniform from minus pi to pi, what's the value of this? Anyone? So this will be like cos phi multiplied by the density function d phi plus j fine. So what will this be? Anyone? Hello?
0.
Yeah, this will be 0. So the whole mean is 0 of this process. So let's look at the autocorrelation function. So autocorrelation function of x, t1 comma t2. So we'll put it this way because our WT is non-stationary. Anyway, so this is xt1 multiplied by xt2 star. Why did I put star? Because x of t is a complex process, right? E raised to j wt1 plus phi e raised to minus j wt2 plus phi. So notice that phi goes away when you multiply, so you get e raised to j. I can write it like this. So let me call this to be y, or we call the other way if you want. So y is, it doesn't matter, wt2 minus wt1. So anyone, what can you conclude about y? Y is of course a random variable because one random variable minus another random variable. But what kind of random variables are wt1 and wt2? Anybody? Look at here, you have to use a Gaussian, right? Because, or normal, because using the central limit theorem, we concluded that the W of t is a Gaussian process. So this is Gaussian minus Gaussian. So what happens Gaussian minus Gaussian? Hello, if X and Y are Gaussian, what is the, remember we went through
Gaussian. It's
What?
Gaussian.
Gaussian, right? Because any linear combination is Gaussian. So we conclude that Y is Gaussian with the mean 0 because each mean is 0. The question is what is the variance of Y? So let's do that. This is just like your homework, except so sigma Y squared is expected value of Y squared because Y is 0 mean. So that's expected value of WT2 minus WT1 the whole squared. So if you expand, you get WT2 squared plus W squared T1 minus 2 WT1 WT2. W is a okay, so like this. So anybody, what is the value of W squared WT2 squared? Anyone? Look at, so we can use this expression RW, yeah, right, because RWT1 comma T2 is alpha T1, which is alpha T1 if T2 is greater than T1, and alpha T2 if T2 is less than T1. Right, this is W squared means you can, this is T1 comma T2 comma T2. So this is alpha T2, this one, alpha T1. And how about this? Anyone? T1, T2. It's here. This is expected by. So remember the way I've taken T2 to be greater than T1. So this is 2T1. So look at here, alpha T2 plus alpha T1 minus 2T1. So the sigma Y squared will turn out to be T2 minus T1. If you take T1 to be greater, so you'll get to this one. Then it will be T1 minus T2. So this is tau. So we have Rxx T1 comma T2 is expected value of e to the power j y. Now how do you, but we just computed that y is 0 mean normal with variance, where is it? Variance equal to, there was an alpha somewhere, right? Yeah, there is an alpha here. So the variance is alpha tau. So variance is alpha tau. So anyone, how do you plug in this here? So remember, Y is Gaussian, and this looks like what? Anyone? So you have to use probability to proceed with the thing. This is a function we have studied in for a random variable. Anyone? If I put omega here, what is characteristic function evaluated at omega equal to 1 for Y. So omega equal to 1. And remember, the Gaussian characteristic function is e raised to minus sigma y squared omega squared by 2. But omega is 1, y is here, so you get e raised to minus alpha tau by 2. This is the autocorrelation function of y. Look at here. We started with, we didn't know this. We assumed that it may be non-stationary, but finally it turns out to be a function of T1 minus T2. So we conclude that x of t is Whiteson stationary at least. And remember, I don't know whether you remember last week, towards the end I showed that if x of t is Gaussian and Gaussian, then Whiteson stationarity and Strickson stationarity are the same. And here x of t is not Gaussian, w of t is Gaussian. But w of t is a Strickson stationary process. Actually, you can also show that in this case, the x of t is also a Strickson stationary process. But at least you can prove here it is Whiteson stationary. Any questions? So this is sort of related to your homework. So I'm going to quote a result from So memoryless system. So memoryless system is simply squaring it or taking the logarithm. So I'm going to call it g of x of t. So this is a stochastic process with autocorrelation function rxx t1 comma t2. So there is a I'm not going to go over the derivation. It's in my lecture 14. So the important thing is the following. So remember, memoryless means it could be nonlinear. So if you pass a Gaussian through a nonlinear system, generally you are not going to get Gaussian. But what is interesting, let me come over here. I'm just looking at my notes. I'll tell you which page, etc. And later you should read it. So on page 13 onwards, systems with the stochastic inputs, memoryless systems come up in page 15, 16, etc. So there is a proof there showing that. So this is the theorem. Let me just state the theorem. I'll state the result. If x of t is a stationary Gaussian, then the y of t is, then we are just going to show that, we are not going to show, but I'll write the result. So this is the result. So first of all, if it is a stationary Gaussian, because there is no time involved, memoryless means whatever is the input, immediately a nonlinear function comes out at the output, like squaring or logarithm or whatever. So you can see, if this is stationary, this is going to be stationary. That's easy. Yt is stationary. But I'm sorry, by stationary I meant the strict and stationary. This is also strict and stationary because no stationarity you are just taking an immediate function of the whatever is the value. So the statistical properties remain the same. But now what is not clear is how do you find out r, y, y, tau. So in general you have to do the problem, but if the input also happens to be Gaussian, this is the cross correlation function. So the cross correlation function, I don't know whether we discussed the cross correlation. Cross correlation function is rxy t1 comma t2 is expected value of xt1 yt2 star. Tau means here it also depends only on t1 minus t2, and so if t2 is t1 plus tau, that's what this is. So what the theorem says is that if the input is strict stationary or stationary Gaussian, then the cross correlation function is proportional to the input autocorrelation function. So now look at the previous result. We had e raised to j w of t plus phi. This was the output, right? I'm sorry, this is the output. Input was x of t was w of t. So this is w of t was w of t is stationary Gaussian. No, I'm sorry. W of t, of course, is not a stationary Gaussian. So this result doesn't apply here. But this is a result that may be useful generally to find out the Gaussian property. So if you want to check a process is Gaussian, and if it is stationary, then you can pass it through a nonlinear system and see whether this relation is satisfied. If you are curious what eta is, that happens to be g expected value of g prime x. So let me go to the main topic today, unless you have any other questions. And so the main topic is stochastic processes applied to linear systems. So as electrical engineers, most of us, this is a receiver design, right? You have a linear system. You apply an input, you get an output. So we remember, input is a collection of waveforms. Each waveform you'll get a different waveform. So if you know the input to statistics like the autocorrelation function, so the first question is what is the output autocorrelation function, etc. If you have stationarity here, what do you have stationarity there, etc. So what's a linear system? Remember, so generally I am going to write y of t as L of x of t. So this is linear, as you know, if L of a1 x of x1 of t plus a2 x2 of t is a1 linear L of x1 of t plus a2 L of x2 of t. So this is y1 of t, this is y2 of t. In other words, if you apply two different inputs and you take the linear combination of the inputs, the output is the same linear combination of the respective outputs. This is linearity. Let me also bring in another property, time invariant. In fact, we are looking at linear time invariant systems. A system is time, it's a system property. What it says is, if you apply some input x of t, and if you get some output y of t, and suppose that you delay this input by some time, like right here. So this is what is input is now x of t minus t naught, applied to the same system, L. So y of t is L of x of t. So you apply a delayed version of the input to the same system, then you don't have to do the same experiment again. What it says is that the output is going to be the new output, y1 of t or y0 of t will be simply the delayed version of the this input. So that's the, in other words, the L of x of t minus t naught. This output is, you can get it from here. Now, what happens if you combine 1 and 2? So that's what it is we have to see. So in other words, let's say you have a, so we are going to look at linear time invariant systems. Systems with both these properties. So remember what is linearity. I just went through this. The output is linear combination of the corresponding outputs, linear combination of the output. Time invariant means if you do an experiment today and you get some output, and if you come back and do the experiment tomorrow, the output will be the same as today's input, but delayed by 1 day. That's what the system doesn't change the output by time. It is insensitive to time. What if you have both the properties? So you have a signal x of t. I'm going to apply it to a system which is both linear and time invariant. How do I write this? So to do this, let's see what is the response of this system to a delta function. So remember, delta function is like this. So depending on the system, you'll get some output. I'm going to call this h of t. So because the system is time invariant, if I apply a delayed delta t minus t naught, here of course you are going to get ht minus t naught. So question is what happens, how do you write this one? So I'm going to show that you can write this in terms of h of t. That's the whole point here. So x of t, the first thing is x of t, if I make this into small segments, and call this value x of, let's say this is ti here, I'm going to call x of ti to be ai, then this waveform, I can write it as a collection of the x of ti multiplied by delta of t minus ti, right? In other words, this is a delta function multiplied by this value. So this is like summation ai delta of t minus ti. I can approximate this, and I make the summation really large, and so that this waveform is approximated by this. So y of t is now linear system applied to x of t. X of t is here, a linear system applied to summation ai delta of t minus ti. But the summation, and because it is linear, the summation goes outside. Look at here, you have two terms. This is summation. So summation of the input is sum of the outputs with the same multiplication. So ai L of delta t minus ti. But this is, look at here, this is delta of t minus ti, ht minus ti. So I can write this as, the summation becomes larger and larger, it becomes an integration. X of ti multiplied by delta of t minus ti dti. Or I change it to tau. So the first thing to note is, I'm going to rewrite this in the next slide. If the system is LTI, everything about the system can be represented by this quantity. This is called the impulse response, because look at here, you are putting an impulse at the input and you get an impulse response. So that has all the information about the system. This waveform has got all the information about the system. If you look at the last line, output due to any input is captured by, this is H, delta L applied to delta H, L applied to delta HTA minus. So let me write it here. So Y of t is integral AI L applied to delta minus delta of t minus tau. So that's going to be H of t minus tau. And this is X of tau in this notation, d tau. This is what we meant here. This xi is whatever is this with the delta tau multiplied by the x of ti is, or ai is x of ti multiplied by delta tau, which is this area. That's what I'm going to call ai. So if I put it back this, which if you write it as and if it is a discrete system, I might as well do it here. If you apply xn, and if this is linear time invariant, the output yn is sigma hn x of or hm x of n minus n convolution. So this is a continuous convolution. This is a discrete convolution. Okay, so this is the waveform. The question now is what happens when the input is a stochastic process? What is the the nature of the autocorrelation, etc., at the output and cross correlation function? So a linear time invariant system with impulse response h of t gets an input x of t. I'm going to call y of t. So y of t is h of tau x of t minus tau d tau. First of all, this is easy to see. So let me get this result out. If this is strict and stationary, what does that mean? That means the density function evaluated at the time instance t1, t2, tn is the same as if you shift it x1, etc., xn, t1 plus c, etc., tn plus c. So we are if you shift the time, the density functions are the same. So corresponding to x1, let's say corresponding to these time instants. So remember, you have two stochastic processes. So this is x of t. You have another one, y of t. So you take a set of time instants, you get x1 through x, this is t1 through tn. These random variables are x1 through xn. The same time instance, you get y1 through yn here. This is y of t. And then you shift it by c, and you get a new set of random variables here and here. I'm going to call this x1 prime and xn prime. These set of random variables have the same density function. That's what it is true. Now, so you have, if you look at f y1 etc. yn and y1 etc. yn, they look at it. They correspond to time instance t1 through tn. Then you have the new random variables here, y1 prime through yn prime. They also correspond to time instance t1 plus c, t2 plus c, etc., tn plus c, because everything is shifted by c, right? So what is the, so to find this density function, we can do what we studied in the previous, before the midterm, I guess in the last lecture at school. So you have y1 etc. yn corresponding to t1 plus c, etc., tn plus c. So this will come in terms of the Jacobian of the transformation, 1 over the, but remember, look at the transformation. The transformation is here linear, and so you can see the yt1, yt2, etc. depends on, where is the, so yt1 is, look at here, h of tau, x of t1 minus tau d tau, etc. ytn is h of tau, x of tn minus tau, etc. d tau. So if you take the joint density function, you need the Jacobian of this transformation, which is which will depend on, just on this h's. And you can see from here, this t1 through tn only depends on the properties of this xt1 through xtn. So, and they are strict and stationary. And remember, this is insensitive to these times. So it is, if you go through this, this will turn out to be 1 terms of the Jacobian multiplied by this density function, which is the same as this. Bottom line is these two will be equal, saying that strict and stationarity is transferred to the output, which makes sense. This is insensitive to time. So whatever is happening here, that property is maintained at the output. So strict and stationary input, linear time invariant system, you get strict and stationary. It doesn't matter which process. So if this is Gaussian, remember, if this is Gaussian, because it is linear, you will get Gaussian. So you also have the Gaussian property. Look at the output. Input multiplied by some constant and the summation. So if this is Gaussian, this will be Gaussian. If these are jointly Gaussian, these outputs will be jointly Gaussian. So Gaussian translates to Gaussian. Strict and stationarity translates to strict and stationarity. The process doesn't have to be Gaussian to, this could be true differently, and the Gaussian could be stationary or non-stationary. Of course, Gaussian stationary means it's strict and stationary. Strict and stationary will give you strict and stationary here. So the bottom line is what? Gaussian, any type of stationarity is the same as strict and stationarity. So you get at the output also strict and stationary. Question is, what if a process is not Gaussian, but just a process and White's and stationary? So let's look at it. So what can you say about y of t? Remember, just look at here. We just concluded that if it is strict and stationary, the output is strict and stationary. So the question is, so again, linear time invariant system. And so this is, so let me take more general. Let me assume that for the time being, input is not even stationary. So I'm going to assume it is just this. So notice that I assume the way I wrote it here, the input could be complex stochastic process, and it is not even stationary. I'll come to this a little later. So let's look at the cross correlation function. We'll go step by step. What's the cross correlation between y and so this is expected value of x of t, t1 multiplied by y of t2 star by definition. Look at the star for the complex case. If this is complex, this could be complex. So remember, y of t is of course integral x of alpha, x of t minus alpha d alpha. So I'm going to put here t2, this will be t2. I'm going to plug it in here. So rxy t1 comma t2 becomes integral, not x, this is h of alpha multiplied by expected values of x of t1, x of t2 minus alpha, d alpha. So notice that this is rxx t1 comma t2 minus alpha. This is star, right? Because this is star. I'm going to plug it in here. So this becomes star. So I'll write this as h star of alpha rxx t1 comma t2 minus alpha d alpha. So this is the convolution on the second variable. So I can write this as rxy t1 comma t2. If you want, you can write it as rxx t1 comma t2 convolution on the second variable. So this will be h star of t2. Look here, this alpha, this is convolution is on this variable. I forgot to do the mean. We'll do it in a second. Let me go through this. Integral is from minus infinity to plus infinity. So this is one result you should remember, or you should be able to figure it out. Now, let me go through this, then I'll come back and do the Whiteson stationary case. So let's continue and do RYYT1 comma T2. The output autocorrelation function is expected value of YT1, YT2 star. For YT1, I'm going to substitute x of beta, h of t minus beta for the other way. Expected value of h of t minus beta, x of all I did was for y of t1, I applied this expression, except not to confuse, I put a different dummy variable here. Instead of alpha, I put beta. YT1, so this will be t1. That's what I wrote. This will be t1. This is YT1, x of t1 minus beta, h beta, d beta. And the expectation is only on the h terms, so the e term. So x term I meant. So this is t1 minus beta multiplied by y t2 star h beta d beta. But this is, look at this, this is rxy t1 minus beta comma t2 integral h beta d beta. So you can see this convolution is on the first variable. So I can write, if you want, this as rxx t1 comma t2 convolved with ht1. So let me write it in the next slide so that you can see. So we had rxy t1 comma t2 to be rxx t1 comma t2 star h star t2, and ryy t1 comma t2 is, I just had rxy t1 comma t2 Look at here, I've got, this is RYY T1 comma T2 is RXX, I'm sorry, RXY. So RXY T1 comma T2 convolved with the first variable, which is T1. So this will be HT1. So if you, this is what we were looking for. The output is going to be, if you combine together, it is RXX T1 comma T2 convolved with HT1 convolved with H star of T2. So that's the expression in the most general case. So if the input is not Whiteson stationary, the output doesn't have to be Whiteson stationary. So I forgot to do the mean. So what about the mean, Y of t? Remember, Y of t is what? Integral h of tau x of t minus tau d tau. So expectation is only on x. So this is integral h of tau x of t minus tau d tau. But this is mu of t minus tau of x. So this is a mu of t minus tau multiplied by h tau d tau. So in general, it will be a mess. If the input is not stationary, then the output also doesn't have to be stationary because it's a function of t. So we have these three key results. Okay, the first result is this. The mean is this one. Cross correlation is this. This is the output autocorrelation. In general, these are there in my notes. I'm just going to go through this. So let's look at the interesting thing. What if so this is the question we want to answer. Suppose x of t is Whiteson stationary. This is given to us. That means the mean of x of t is a constant and the autocorrelation only depends on tau. What can we say about the stationarity of y of t? Remember, we are only talking Whiteson stationarity here. Strickson stationarity we already answered. X of t is Strickson stationary, then the output is Strickson stationary. So that is not the question anymore. So the question is, what is the, so to answer this, I'm going to use, I don't have to rederive, I'm going to use these results. So let's look at answer. So let's look at expected value of y of t. So it's already here. Expected value of y of t is, if you look here, it's a mu x of t convolved with h of t, right from here. So I'm going to write here, it is going to be a mu x of, I have t minus tau, but mu x is a constant, so that's just a mu, t minus tau, just mu, multiplied by h of tau d tau. So mu x goes outside. So this is h of tau d tau. That's just another constant. In other words, you get a constant. So the output is a constant. Output mean is a constant if the input mean is a constant. So let's look at, then we can use, so how about Rxy T1 comma T2? answer is here. I'm just going to use this rxy, rxx t1 comma t2 convolved with this on the second term, right? That's what this is. So I'm going to expand that and see what happens. So this is integral rxx t1 comma t2 minus beta h star beta. That's what we mean by convolution. Now remember, this is Whiteson stationary. That means this is t1 minus t2. X is t1 minus t2. So I'm going to make this t1 minus t2. So this will now read rxx t1 minus t2 plus beta multiplied by h star beta d beta. But this is tau. So this reads minus infinity to plus infinity rxx tau plus beta h star of beta. Does anyone know how to express this in terms of convolution? Anyone? This is some sort of, if it was negative here, it would be convolution, standard convolution. What is this the convolution of? Anyone? So if you take the function h star of minus tau, this is what it will work out to be. This is actually the convolution of Ipo with a minus sign here, because this will become minus tau minus here. So change minus to plus, will become plus here, plus here. That means, look here, the right side is only a function of tau. So this must be only a function of tau, which is clear from here. So we can write that the cross correlation is jointly Whiteson stationary. X of t and y of t are jointly Whiteson stationary. That's the result from here. How about the output ryy t1 comma t2? So again, the result is here. Ryy is expressed in terms of the joint cross correlation function convolved with ht1. So that's where I'm going to go. So this is rxy t1 comma t2 convolved with ht1. So let me expand this. This is rxy t1 minus alpha comma t2 convolved with ht1. Not ht1, alpha. D alpha. But this is, we just proved, that rxy t1 comma t2 only depends on t1 minus t2. This is only, so this must be t1 minus t2. So this you can write it as rxy t1 minus alpha minus t2. I'm going to write it like this, multiplied by h alpha d alpha. But this is once again tau. So this now reads rxy tau convolved with h of tau, because it depends only on tau. So output is also Whiteson stationary. But this is already rxx tau convolved with h star of minus tau convolved with h of tau. So if you call this to be rho of tau, you can also write it like this. So what's the summary here? So the moral of the story is, if input is Whiteson stationary, where is it? If input is Whiteson stationary, then the cross correlation function is jointly stationary, and the output is Whiteson stationary. And the output autocorrelation function, you can write it in terms of the cross correlation function, or in terms of the input autocorrelation function convolved with h of tau convolved with h star of minus tau. Remember, convolution is commutative, so you can write this as h of tau convolved with h star of minus tau, etc. Any questions? So let me summarize what we have done, because this is an important result. If it is strict and stationary, the output is strict and stationary. You can find a little more elaborate proof in my book, so you should look at it. But what we have just said is, if it is whites and stationary, the same system, then the output also is whites and stationary. So if this is Rxx tau, this Ryy tau is Rxx tau convolved with h of tau convolved with h star of minus tau. But moreover, they are also jointly whites and stationary, the input and output. That's going to be Rxx tau convolved with h star of minus tau. So that is sort of where we are now. So we know that if the process is input is whites and stationary, and then the output is whites and stationary. If the input is strict and stationary and the system is linear, then the output is strict and stationary also. Any questions before I proceed? Hello? Anyone? Is anyone there?
Yeah, we are here listening.
Okay. So this is in my lecture 14, and also in my book, it is there. So you call a process to be white noise. So what is white noise? You have a process. If you take one sample from T1, other sample from T2, it doesn't matter where T1 and T2 are there, their correlation is 0 if T1 is not equal to T2. So they are always uncorrelated. T1 equal to T2, you will have some variance. So the autocorrelation goes like this. It's a function of T, but sometimes the variance could depend on T1. If this is not a function of T, then it is stationary white noise. So whites and stationary white noise is where autocorrelation is some constant multiplied by this. Autocorrelation looks like this. So if you apply a white noise, stationary white noise, look at the output y of t. So according to what we said, this is Rxx tau convolved with h of tau convolved with h star of minus tau. But this is simply delta of tau. Anybody, delta of tau convolved with any h of tau, what do you get? Anyone? If you convolve a delta function with any function, what do you get? Function itself, so that you get this property. So my point is, if you excite the system with the white noise, what the autocorrelation function of the output only is a completely system properties. You can find out all the system properties from this autocorrelation function. Stationary white noise. So if you don't want to distract the system, this is a non-interrogative a test procedure. If you want to find out the system characteristics, you excite it with white noise, then look at the autocorrelation function. That's going to give you the poles and zeros about the system. We'll talk about this later when we do the power spectrum. So this is done in stock market a lot. So if a function, if a stochastic process is like this, a lot of variations. So this is x of t. You can see a lot of change. Sometimes you may want to smooth by taking a window. This is called a moving window. Let's say from some time you go wherever you are, you go a window of minus t this way, minus t this way. So from x of t, you can create a window like this. You can create a new process. So you can see you are just averaging here. You can also write, by change of variable, you can also write this as like this. So whatever is the value, you go over a moving window. That's why it's called a moving average. You can do discrete values or continuous values. So what is the question now? Question is, what is the autocorrelation? So this type of problems can come up in the exam in couple of 2-3 weeks later when we do exams on this. So even homeworks you should be able to do it. Remember, stock guys do this, right? They plot the moving average on top of this, saying that this is 50-day moving average, right? And then maybe, so you can see this will be a little more smoother compared to this. Then using the trend here, you try to predict what is going to happen to the actual stuff, etc. So this is y of t. So if x of t is 0 mean, anybody, what is the mean of y of t? Anyone?
Also 0.
Yeah, if x of t is 0 mean, then y of t is 0 mean. So let's find its autocorrelation function. Say, let's say x of t is Whiteson stationary. So y of t mean is 0, of course, if x of t mean is 0. Otherwise it will be the same thing, right? Y of t mean will be what? Expected value of y of t is 1 over 2t. The expected value of x of t minus tau. But this is a constant mu. And so this will come out to be the same one. So the mean doesn't change. But it is a smooth process, so we want to know what's the autocorrelation function. So let's look at RYY T1 comma T2. We don't know whether this is stationary, so we are going to write it like this. So this is expected value of YT1, YT2. I don't have to put star here because this is just a window, smoothing window. Everything is in real time. Also, I'm going to substitute. So this is expected value of 1 over 2t. What is it? X of, what was it? X of t1 minus alpha d alpha. And this is t1 minus, let's say, tau 1. And this is another window is x of t2 minus tau 2 d tau 2. This is minus t to t, minus t to t. So I'm going to pull out the integrals outside. 1 over 2t the whole squared. Expected value of xt1 minus tau 1 multiplied by xt2 minus tau 2. So you should be able to do things like this next week. I mean, this homework, etc. So this is how you develop the skills. But remember, this is given to us. This is this is the autocorrelation function of x sub t. So what will be the argument here? Anybody?
T1 minus tau 1, T2 minus tau 2.
Look at this. X of t is a Whiteson stationary process. except T is a Whiteson stationary. So this will be equal to, what will come here?
T1 minus tau 1 minus T2 minus, plus tau 2.
You can write it like this, right? Yes?
Yes, Professor.
All right, I'm going to call this T1 minus T2 to be tau. So this term, I'll write it in the next sheet. So look here, I just wrote it there. This is tau. This is tau. These are just variables of integration here. So it should be clear to you now that this process is, I can write this as RYY tau because it only depends on tau. These are to be integrated. So let's see whether we can simplify this further. So this is your tau 1, this is your tau 2. So I'm going to call this to be a new variable. So you all remember, in this tau 1, tau 2 domain, you are only integrating along T1 minus T2. So I'm going to call this T1 minus T2 to be a new variable. And let me call it to be a T. So this expression now reads 1 over 2T whole squared. This is from minus T to T, minus T to T. Rxx tau minus T d tau 1 d tau 2. Let's see whether we can get rid of this d. So we are integrating along this line, tau 1 minus tau 2 equal to T. So we are only integrating this. So another way to integrate is because only the variable tau 1, tau 2 matters. So we are integrating. So all along this line, tau 1 minus tau 2 is the same. So I take a small strip here. I draw another line. Tau 1 minus tau 2 equal to T plus delta T. So then I need to, if I can find out this area that I have shaded, then I can just integrate along along T here in this way. So this new integral will become one integral from minus, T will go from this edge to this edge. This corresponds to T1 minus T2 equal to minus 2T to plus 2T. So this will be Rxx tau minus T. So let's see what comes up here. Multiplied by this area. To find out this area, let me find out the area of this one triangle minus another triangle. So the area of the big triangle is, look at here. So we need to figure out this side. So let us look at where this meets the line. You put tau 2 equal to 0. So you get tau 1 equal to T. So this point is T. And this point is T, right? This is capital T minus T, capital T. Because look at here, tau 1 goes from minus T to T. So tau 1 goes from minus T to T. Tau 2 goes from minus T to T. So I hope you see this. This small distance is T minus small t. So this distance is capital T minus T, which is the same as this. I will, maybe I'll write it here. So take this line. I'm saying, look at this point. This point is T1 minus T2 equal to T. So when you put T2 equal to 0, you get this point to be T. So this small distance is T minus, this is capital T. So this small distance is T minus T. So this distance is...
See the bottom.
Oh, yeah. I guess I will. Yeah, this is clear. So this is tau 1, tau 2. This is tau 1 minus tau 2 equal to t. So when you put tau 2 equal to 0, you get this point to be t. This is capital T because we go from minus t to t. So this distance is t minus t, which is the same as this t minus t. So this distance is t because this is so this is t minus t. So that is 2t minus t. So this is the same. So the area of that triangle is half 2t minus t. So the area of this small thing is minus half 2t minus t minus delta t squared, right? Base into altitude multiplied by half. Base into altitude multiplied by half, because there is another line here. So if you take the difference, the first term cancels away. The middle term is 2t minus t. And the last term is multiplied by delta t. The last term is delta t squared. This I am going to cancel. So essentially this area is just this. So I come back here. I substitute that area here. That area is 2t minus t multiplied by delta t. Remember, this is just a dummy variable, and this line could be on this side or this side. So there is an absolute value here. Let me take 1 2t inside. So this reads now minus 2t to 2t rxx tau minus x if you want. 1 minus absolute value of x over 2t dx. I just changed the dt to x. So this is the answer for ry by tau. So this is like a window, a triangular window. So if you want, we get ry tau is rxx tau multiplied by or convolved with a triangular window TR of tau. This is like this window of width minus 2t to 2t. So that's the effect of. So we will see later how to express this also, how to express this differently. That's the effect of moving average. So in the stock market, etc. If you to smoothen a stochastic process, you can take the average. So the question is, what is the autocorrelation average function? I just found it out for you here. So the moral of the story is, if the x of t is stationary, then the y of t is also stationary, and it is the autocorrelation is the convolution of the original autocorrelation function convolved with a triangular function. So that's the smoothing on the triangular function. Any questions? So in the notes, I have something called up crossings and down crossings. I'm not going to go over that. These are maybe when we have, if we have time later, I'll do it on on another day. Now let me talk about the discrete processes for a little bit time. Discrete time processes. That means for whatever reason, we are only going to observe this at time instance t1, t2, etc. Sometimes this, if you have sampled the process, this will be just multiples of t. So you have a random variable here, you have a random variable here. You may have an underlying process, whatever, but observations are only corresponding to. So we only define it for these values. So I'm going to call it xn to be x of t, maybe sampled at t equal to, let's say, nt. So again, the mean of xnt is just mean of n. It's the same way again. So this is mu xn. If the process is Whiteson stationary, this is a constant. And the autocorrelation function is, instead of t1, it is n and m, two indices. So this is going to be x of n and x of m star. Once again, if it is a function of n minus m, we call it to be Whiteson stationary, etc. So you can do discrete average also. So this will be exactly the same process will go through. This is a smooth over a window, but you can also scale it and smooth. Anyway, so we already know there's no difference if you process, so we know the results. If you process this through a linear time invariant system, you will get exactly the same results. If this is Whiteson stationary, this will turn out to be Whiteson stationary. And the output to mean will be a constant because it is simply summation hk, expected value of n minus k. But this is a constant, so this is simply another constant. And you will get the same result again. The cross correlation function is going to be, I'm going to leave it to you to show rx x n comma m convolved with discrete convolution with h minus m star, and ryy n comma m is rxy n comma m discrete convolution with hn, the first variable. And if this is Whiteson stationary, then you will get rxy n is rxx n convolved with h star of minus n, and ryyn is rxyn convolved with h of n. You proceed exactly the same way. So I'll show you one of them. So for example, rxy n comma m. That's by definition expected value of xn y m, right? So this is expected value of xn summation hk x star of k m minus k. So this is summation hk star, right? Hk star expected value of xn x star m minus k. So if this is Whiteson stationary, this will be rxx n minus m plus k convolved with h multiplied by hk. N minus m I'm going to call a new variable. Anyway, it's n minus m. So that you can see, if this is Whiteson stationary, this will be a function of n minus m. So you get rxy. Let me call this to be a new variable I. Then this only depends on I. So this is going to be summation hk star rxx I plus k. So that's the convolution of rxx I and h minus I star. Similarly, ryy, same thing. ryy n comma m is expected value of yn ym star. Yn I'm going to write a summation hk x n minus k y star. But we just showed, the expectation is here, we just showed that this is only rxy n minus m minus k. And if I call this to be I, this reads, if I take this expectation within, so this is summation hk rxx I minus k. So that's just the convolution of rxy here, right? X and y. rxy I convolved with hi. But in the previous page, we showed Rxy, I is Rxx convolved with this. So you get the, so this also depends only on I. Or if you change I to n, you can write it like this. And Rxy is Rxxn convolved with hf minus n. So I can write it as hn convolved with hf minus, h star of minus. Same result as in the continuous case. So continuous case or discrete case, these properties are true. Any questions? Let me again show you one more property of these autocorrelations. Maybe we did discuss last time. So if I say, let's say Xn is a discrete time process. Actually, we'll bring in White's substitution later. So let me define Y to be summation AI xi. So this is a new random variable. So if I look at expected value of y squared, this is positive. Anybody? Why is this positive? Why is expected value of y squared positive? Hello?
Because y squared is positive always.
Yeah, because this is definition is y squared multiplied by density function of y dy. Everything is positive here, so this is positive. But let's plug it in. This is going to be summation ai xi y squared multiplied by another summation aj xj absolute value star. So if I collect the summations, one is on I, one is on j, I, j, ai, aj, they are constants. Expected value of xi, xj star. So this is, I'm going to write it as rij. If it is stationary, it will be ri minus j. So you get this property, summation ai, aj star, rij star. So this is non-negative. So, but you should go home and show, this is where the matrix algebra comes in, that this summation ai, aj star, rij, you can write it like this. So this will be R11, R12, etc., R1n, R21, etc., R2n. I'm going to call this the covariance matrix R. This will be A1 star, A2 star, etc. So you can write this as A star or A, and this is non-negative. Everything is the property of this matrix. So I'll go over this in detail on Saturday. That's why the matrix algebra becomes. So we call this to be a non-negative. This is a proper. This is not the property of A. A is arbitrary here. So the covariance matrices, if you arrange it in this form, and remember we also have this property, Rij is the same as Rj I star. So if these entries are complex conjugates of each other. So we will go over this, and if it is stationary, what happened? This becomes the difference, right? Rij becomes Ri minus j. So if you write that up, so if Xn is Whiteson stationary, the covariance matrix will look like this. R0, R1, etc., Rn. R here this will be the complex conjugate of this R0. So you go home and see, you are already at home, but see whether later you can get this. And this matrix is called the Toeplitz matrix because all its diagonal entries are the same. This is all R1 star, this is all R0. Next one is R1 star, etc. So this matrix is called a Toeplitz. Again, I'll go over this Saturday. And non-negative matrices. So what am I trying to say? If a discrete stochastic process, covariance matrix is Toeplitz, and it is non-negative definite. And there is more to it. And I'll go on the properties on Saturday. What I want to do next, we have about 1 hour. I want to start on linear estimation. This is a long topic. It will take us most of next week. So I want to do a simple part today based on this is also useful for ML, what do you call, machine learning, etc. Concepts. So I'll start with the so given a set of random variables, these random variables may come as the observations of this. How to estimate some underlying parameter, an underlying variable or parameter, theta. So what I'm going to show you is, you will see how useful the things you have studied is. So let's do a 2-3 minutes break. Let me just drink some water and come over. So we'll start right now. Any questions so far?
Professor?
Yeah.
So what kind of a matrix is a Toeplitz matrix?
What do you mean?
So what properties does it have?
Remember, Toeplitz matrix is only one property. All the diagonal entries are the same.
So it doesn't have to be like a complex conjugate for some elements?
No, I mean, just a Toeplitz, if you just say Toeplitz,
Yeah.
it's so whatever is this entry C0, all the diagonal entries will be C0. If this is C1, all this will be C1. C2, this will be C2. Last will be Cn. This will
Is
be
it also symmetric?
It doesn't have to be. I mean, just the Toeplitz is, of course, if you say symmetric Toeplitz, then these two will be the same, right?
Right.
So if you just say Toeplitz, Toeplitz simply means all the diagonal entries are the same. So what I am trying to say is, you have a practical application here. So what we have, the theorem is, if a discrete time stochastic process is Whitson stationary, then the autocorrelation matrix turns out to be Toeplitz, and it is symmetric, and it is positive definite, non-negative definite. All the three properties are here. This is Toeplitz, also symmetric, because the covariances have these properties, symmetric. And the third one is it is non-negative definite. So that's what I wanted to. So you can, you should read up a little bit on Toeplitz matrices if you want before you come up. What sort of properties are there? But we also have non-negative definite Toeplitz matrices which are symmetric. Anybody else has any questions? Yes. So I'm going to we only have about 45 minutes today. Right. So I'm going to use this to give you some important concepts from statistics. Sushant? So what is the problem here? See, we have some unknown. So we collect, this is data. We collect data obviously related to the unknown. If you are if you're trying to collect data, obviously you want it to collect like today's temperature. If you want to collect the temperature, then you need to devise something which will measure something proportional to that, which is what a thermometer does. So you collect the data from here and there in the city. So these are the, but you know, there is noise involved. If whatever you collect is a complex process. So the data you collect, whatever form, it has something to do with the unknown. That's the whole point. And it may come from a stochastic process. So here the stochastic process is spatially distributed. Remember, atmospheric changes, this and that. So you are collecting the temperature at LaGuardia, Central Park, JFK, etc. You can think of that way, or you can think of this as observations at a different time instance. Whatever is the t variable, it doesn't have to be time; it could be also space, etc. And then, in principle, of course, these being random variables. Remember, these random variables are at time instance t1, t2, etc., tn. But I want to put theta here because to show that these random variables have something to do with what you are collecting. So this is the whole point of the big problem of design of experiments, right? How do you design so that you collect, you don't collect nonsense data? Think of all the particle accelerators. They spend billions of dollars. So the whole design is on design of experiments, how to perform an experiment so that whatever you are looking for, you can detect its properties and then conclude one way or the other way. So this is a big subject, how to collect the, so we are going to assume that we are smart enough to collect the proper data. So the data contains some information about the unknown. Of course, if the data has no information about the unknown, it is garbage for your problem, right? And moreover, they have some joint density function. So the big problem next week is, so I'm going to assume that right now I know this function. So you may say, look, I don't have no idea about this density function. So don't give me any method which will depend on the density function because I have no idea. If that is the case, then we have to do something else, which will be the topic next week. So today I'm going to give you a quick review what statisticians do if you have a little more information about the, and you can see how useful are the techniques we have learned in the first half of this course. So look at this problem. The data has been measured. So what is the variable here? Anybody? In this joint density function, what is the unknown? Anyone?
Data.
Only theta, because you know the time instance, because you know when you made the measurements, and you have the values. So this is only a function of theta. So this idea is due to Fisher. He is supposed to be known as the father of statistics, I think from last century or the century before that. So his idea is that you bring in this joint density function of all this data and plot it. So it is going to be something like this. Remember, it's only a function of theta actually, because these are measurements. They are already there. What are you looking for? Anybody? What are we looking for? So this is obviously plotted as a function of theta because that's the only unknown. What are we looking for here? What is the whole purpose of collecting the data?
Future values of theta.
Yeah, to find out the value of theta, the best value of theta. So Fisher's idea is that once you plot it, if you are looking for the theta, the best value of theta is suggested by the data. Remember, this is the probability density function. What this shows is this value of theta is the most likely. This value is the most likely. Because for that value of theta, the probability is the maximum. You can look at this. So this is the most likely value of theta. And that's his principle of maximum. This is how the principle of maximum likelihood comes up. This is the, as you might have heard the name, this is a major concept in statistics, like maximum likelihood. So that says if the best value of theta is found from the joint density function of all the observations, which are also functions of T1, T2, etc., Tn, but also function of theta. So this is known as the likelihood function. But you know that that's nothing but the joint density function. This is also known as the likelihood function. So if it has a, you can see sometimes it may have a two peaks like this. So you can see the likelihood. So this is the maximum likelihood solution, but it can have multiple solutions. And moreover, if the function is nice and smooth, how do you find the maximum? Anybody? How do you find the maximum of a function?
Take the derivative and set
Yeah.
zero.
Oh, right. So sometimes you can also, because the density function is non-negative, sometimes it's convenient to plot the logarithm of that. So this is known as the log likelihood function. It will have the same property again, log likelihood function. So again, so this is called the maximum likelihood estimate. So you take the, so if I call this to be L of theta, log likelihood function, you take the derivative of this with respect to theta, substitute it to 0, then you get the maximum likelihood value. So let me do two problems for you, and then I'm going to ask you to. So the first question is, if you find a maximum likelihood estimate, obviously it's going to be a function of in terms of the data. That's the whole point. The unknown is going to be in terms of the data. The data has been collected. So then you can ask, what is its mean, what is its variance, etc. So you are able to do all this now because you already know how to find the mean, variance, etc. So from there we will, so what do you expect the mean to be? What is the best that can happen? Remember, the maximum likelihood is a function of data. If you do what were you looking for originally? You are looking for theta. So what would you expect this value to be? What is the best value this can take? Anybody?
Theta itself.
Theta itself. That's the best you can happen. So if this happens, we call this estimator as an unbiased estimator, another new concept. All this will be useful in machine learning. So this is the unbiased estimator for theta. So the question is maximum likelihood, and what do you expect the variance to happen to? What should happen to the variance? Anybody? What do you, in general, if you make an estimator, what do you want the variance to look like? Large or small? Yeah, 0 will be impossible. So we want at least the variance to be small. So the small or large, you need to compute the variance, and that's where all this what you have learned before helps you. So how to find the variance. So I'm going to do two problems. So let's say x1, x2, etc. xn are Gaussian with the mean mu and variance sigma squared. I'm going to take it 1 as you. So this is a problem known variance, and the mean is unknown. So look how I am going to use what we learned to solve this problem. So you understand the problem. These are the observations. I'm starting with a simple problem. The observations are known to be Gaussian with some unknown mean and variance equal to 1. Sometimes the variance also is not known. So you have two unknowns. So this is most likely the case. Today's temperature is the actual temperature multiplied by some random, added by some random values. And this is how this comes up, let's say. So the mean, if this random stuff is 0, then the mean value is t itself. So the question is, how do you estimate the mean? Let's look at this problem. So remember, I need the likelihood function, which is the joint density function of all of them. If all the observations are independent, what will be the joint density function? Anybody?
The product of individual.
Yeah, so this will be the product of the density functions. Each density function looks like this: 2 pi sigma squared. Sigma squared is 1. E raised to minus xi minus mu the whole squared over 2 sigma squared. Product I equal to 1 through n. So that's the joint density. Only thing we know is the data. We don't know this. So this, of course, you can write some constant 1 over 2 pi sigma squared to the power n by 2 e to the power minus xi minus mu the whole squared over 2 sigma squared. Now I'm going to take logarithm. So I'm going to take logarithm here. So logarithm of the likelihood, that's the log likelihood function, will be some constant log of 1 over 2 pi sigma squared to the power n by 2 minus summation xi minus mu the whole squared over 2 sigma squared. Look at here, two terms. So when you do the logarithm, this will be log a plus log b. Logarithm of exponent is just this, which is what I have. So now I take the derivative of this with respect to theta. So this is a constant, goes away. The derivative of this is, look at here, 2 summation xi minus mu. Then there is a minus 1, and minus minus goes away. Then you have 2 sigma squared I equal to 1 through n equal to 0. So 2 goes away, this goes away because of the 0. And if I simplify this, I get summation xi minus n mu hat ml, because I put mu equal to mu hat ml equal to 0. So I get the maximum likelihood estimator is going to be 1 over the sum of the samples, which is this is what you would do anyway. If you have a bunch of observations, you would add up. But now you have a theorem. The theorem is, if the data is Gaussian, adding the observations is the best estimator for, is the maximum likelihood estimator for the mean. All right, so what is the next one? Next one is, as I said, how good is this estimator? So I want the mean of the maximum likelihood estimator. I want the variance. So again, fortunately from this class, it's easy to do. So look at mu hat ml is 1 over n summation xi, I equal to 1 through n. Anybody, you should be able to do mentally. The mean of this is the sum of the means of this divided by this. So what will be the mean? Anyone? Hello? See, each of the mean of this is mean of this is the mean of this. Mean of this is mu, so this is n mu over mu, n. So that will turn out to be mu. That means this is an unbiased estimator. Expected value of this is another thing. Another observation is if you take, remember, sum of Gaussian random variables is Gaussian. So anybody, the mean of, so this is Gaussian. We can actually include from a previous class. Sum of the mean is the sum of the mean. So that's n mu. What is the variance of this? Anybody? Variance of the sum of independent random variables.
N sigma squared.
What?
N sigma squared.
Right, the sum of the variables, so that is n sigma squared. Now if I divide this by constant, what happens to the mean? Anyone? If I divide a random variable by a constant, what happens to the mean? Hello?
It also gets divided by n.
And how about the variance?
It gets divided by n squared.
So this is what the previous lectures, if you have paid attention, will. So n cancels. You get that the mean is mu, the variance is sigma squared over n. So we have all the answers. The variance is sigma squared over n, which means that if you have lot of observations, this becomes a good estimator. That's the moral of this story. I'm looking at your next homework. You have some, so let me pick up a problem from there. Or I'll do 2 more problems. One your homework problem. And a lot of these things you can also find in my chapter 8 of my book. Some of these examples are there. But so this is the problem. They are exponential with the parameter lambda, but lambda is unknown. So we follow this guy's approach, Fisher's approach. We form the likelihood function. That's the product of the density functions because all of them are independent. So this is going to be 1 over lambda e raised to minus xi over lambda, I equal to 1 through n. I'm just doing it quickly. 1 over lambda and e raised to minus summation xi over lambda. This is where we start. So I'm going to do the logarithm of the L of theta, which is, well, let's say this is a logarithm of this one, the joint density function. So if you do the logarithm, we can do it mentally here. N log lambda with a minus sign minus summation xi over lambda. So we got the likelihood function. Remember, so Fisher's idea is you take derivative so that you find the maximum likelihood estimate. So we take the derivative of dl by d theta to be lambda to be 0. So the d by d lambda of minus n log lambda minus summation xi over lambda. So let's do the derivative. So this is minus n over lambda minus plus sigma xi over lambda squared equal to 0. So if you solve for lambda, this will turn out to be again this. So you have one more theorem. The maximum likelihood estimator for if the unknown is exponential is also the sample mean. I'm going to leave it to you to find out its the mean of this random variable and also its variance. So you can see how useful this problem is. I mean, this what we have studied is this is the way statistics goes. So let me give you a little more serious So how about this problem? You go to library or wherever, you can find out the rainfall for any particular city, let's say over the last 100 years. And the question is, what can you say about those that whole data together? So you may say this is a stretch. You may say I'm going to assume that the rainfall is over all these years uniform from somewhere to somewhere. So the question is, I don't know. Obviously, the lower limit is easy. No rainfall to some rainfall here. But I have no idea what this is. So I just use this model. So what is a best estimate for this? So again, let's see whether we can use the Fisher, this maximum likelihood idea. So what is such? So again, these are, because it is yearly, they're all independent observations. So our joint density function is a function of h, obviously, but that's the product of the density functions. Remember, h is unknown. You're trying to find out from the data. So if this is uniform, it is like this. What's the height here? Anybody? 1 over h, right? So remember, xi is between 0 and h. That means x1 is between 0 and h. x2 is between 0 and h, etc. xn is between 0 and h. How will you put all this into one function? Anybody? x1 is less than h, x2 is less than h, xn is less than h. How do you put this in terms of one inequality? Anyone? If each of them is less than h, what does that mean? Hello?
The summation is less than an h.
Think again. Summation is less than, I want to capture one. It should go both the ways. If each is like this.
The maximum.
Yeah, that's good. So the maximum of x1, etc., xn must be less than h. So let's plot this function. This function goes like, so this is 1 over hn, and remember unknown is h. So it is because h is greater than the maximum. So this value is max of x1, etc., xn. So I'm plotting this function f of x1, etc. So look at this. According to, I just plotted it. So there is nothing. According to Fisher, the unknown, the best value of h is given by wherever this density function peaks. So what's the maximum likelihood estimator for h? Anyone from this graph? Anyone? Is this right? So this is the maximum likelihood estimator. Notice this is no longer linear. So h hat ml, I'm going to call this y, is max of x1, x2, etc., x. So now your problem is to find out the mean and variance. So of course the mean is y multiplied by the density function of y. So you can see how useful what you have learned is. This is, so I'll show you how to find the density function. Let's say we want the distribution function. So that is probability of y less than or equal to y. Remember when I was doing max and min, you were thinking why bother? But you can see now applications in statistics. So y is a maximum of x1, x2, etc., xn less than or equal to y. And then what? Y is, remember each one of them, look at here, each x is between 0 and h. So y also will be between 0 and h. So this is the same. If maximum is less than h, x1 is less than y, x2 is less than y, etc., xn less than y. But they are all independent. So this becomes each one of them, the probability of xi less than y, product I equal to 1 to n. But that's the distribution function of xi, y, the product I equal to 1 to n. But that's just the n to the power of any one of them. Anybody? What's the distribution function of a normal random variable? I'm not normal, uniform. That's y over h to the power n. So we have the distribution function. So fyy is the derivative of that, etc. So now you can use this to find out the mean and variance of this and see. So I'm going to leave it to you to find out. I don't know whether this is a homework, but this type of problems. So that's the general idea of principle of maximum likelihood. This is not a course on statistics, but the only reason I am putting this here is because statistics uses the ideas that you learned in probability. Sushant, are you there?
Yes, Professor.
What time is it?
4:58.
All right, I will do one more problem. So remember, you should do this, complete this problem so that, or going back to this, so as in the next example, let's say x1, x2, xn are unknown. This time the mean is known, but the variance is unknown. So I'm going to call it theta. So again, the principle is the same. You found the joint density function, which is a function of theta, and take the logarithm if you want, and take the derivative with respect to theta, theta equal to theta hat m. That will be the solution. So let's see that. So joint density function. So there will be a few problems of this type in the next homework. This is just a slide to show that what you have learned is useful in many courses, including this type of estimation. So you can see if you estimate these two parameters from the data, and if you know the data are surely Gaussian, then you know the density function completely, because the density function only calls for two parameters. So you estimate both of them from the data. So the joint density function is the product of the density functions. So that's the product of the, we have this density function. Each one of them is Gaussian with, so instead of sigma squared, I'm going to call theta, e raised to minus x minus mu. Mu is known, divided by 2 theta, 2 sigma squared. The product I equal to 1 through n. So this comes out to be 1 over 2 pi theta to the power n by 2 e to the power minus xi minus mu, the whole squared over 2 theta. So let me take the logarithm here. I'm going to do the logarithm. This will turn out to be log of n by 2 goes outside with the minus sign. Then it is 2 pi theta minus summation xi minus mu, the whole squared over 2 theta. So this is your L theta. So I should take the derivative of L with respect to theta. So notice there is a theta here. So this you can write it as log 2 pi plus theta. So 2 pi goes away. So this is minus n over 2 theta, right? Minus here summation xi minus mu the whole square. That's a constant. So derivative of 1 over theta is minus 1 over 2 theta square. This equal to 0 at theta equal to theta hat. So you take this term this side and solve, you get theta hat ml to be 1 over n summation xi minus mu the whole square I equal to 1 to. So here is your problem. I found the estimator. Mu is known. If mu is not known, you use the previous technique and plug it in here. Now we want to find out the mean and variance of this. So I'm going to leave this to you to do it. So you can see how useful the things are, what you have learned in the previous half. So I'm just looking at the next homework problems above. So there will be some problems of this type. So this is what I mean by unbiased. So theta is, the idea is this one. This is known because this is a function of the data. But if you take the expected value of this, this is close to the unknown. It is exactly the same as the unknown. So this is your estimator. Obviously, estimator is known because x1, x2, etc., xn are known. So the expected value of this quantity should be equal to the quantity that you are looking for. If that property is satisfied, then we call the estimator to be an unbiased estimator for theta. Remember, theta is unknown. And of course, if the variance is, this should be, ideally it should be as small as possible. So the question, later questions, I'm not going to do it now. How low can this variance be? And this is where the Kramer-Rao bound comes in, but that's not here. You should take the next year course, Detection and Estimation Theory, where we go into all this in great detail. So this is a deeper question, but you can certainly find the variance. It will be some value. So the question is, are there situations where you can find another estimator which has a lower variance and so on? So what is the problem here? The problem here is if you, so again in a queuing theory, if you find the, as another example, so you have all the, you know that this is from a Poisson process, you see observations. So you take some time instant, you can see how many observations are here. So, and you take some other time instance. So this is X, random variable x1. So this is, you can see how many actually inputs have come. Let's say you take some constant time delta. So we know this is Poisson with the parameter, let's say delta is 1, this parameter lambda, x2 also is Poisson with parameter lambda, etc. So we observe, and the lambda is unknown. So we have observations xi which are from Poisson. Just to give you another example, we don't know. So as I said, this is the way you will do the experiment. You take some time instant, see how many arrivals came in. Take another non-overlapping time instant, see how many arrivals came. Call it K1, K2, etc. This you can observe how many arrivals are there. All you don't know is, so using these observations, we want to find out what's the value of lambda. So according to Fisher, take the joint density function. Because these intervals are non-overlapping, they are the product of the density functions. Each of them is e raised to minus lambda. If the delta is not 1, there will be a delta here. Let's say lambda to the power xi over xi factorial. So if you take the logarithm, you take the logarithm here. So this is logarithm of e raised to minus n lambda. Let's say I equal to 1 through n. This is product of, this is lambda to the power summation xi over product of xi factorial. I need to take the logarithm, which I'll do in the next step. So lambda or L of the lambda is minus n lambda. Look at here, logarithm of this term and logarithm of these terms. The other terms are plus summation xi log lambda minus log of the product of xi factorial. So when you take the derivative of this with respect to lambda, you get minus n plus summation xi over lambda equal to 0. So you get lambda hat ml is 1 over n sigma xi. So this is how in a queuing theory you will determine the parameter of the Poisson process. Again, I'm going to leave it to you to find out the mean and variance of lambda hat ml, etc. So in the next week, I'm going to do the case where we don't know the density function. So you have observations x1, x2, etc., xn, and some unknown, some y is unknown, and how to estimate y in terms of x1, etc., xn. This is the problem next week onwards. You can also read through my lecture notes 16. And so if you know all the density functions, you can go for the maximum likelihood estimate for a parameter. Sometimes what you have, say this is, say this problem. So this is today. Obviously this is, so I'm going to call it T1, let's say T2, I mark it this way. So this is the past. So I have x1, x2, etc., xn from the past, and I want to find out this value. So this is my unknown. So this you can see is future. So this is a problem next week. So obviously stock market or anywhere, this is prediction. Another type of estimation. So of a process, you know some values in the past, how do I find out? But sometimes you may say, I want to find out the value here. So that's in between also. That's also one kind of prediction. Interpolation, right? You want to use these values to figure out the value here. Or maybe long back what happened. That's in the extrapolation. All this will be, so we will address these types of problems next week. Another thing is, so we need some matrix theory here. That's why I want to do the, another thing is, another problem of this type is, say oil exploration, whatever. So to figure out whether there is oil here, you have no idea. You drill a small hole, then blast dynamite, and you put the sensors all over. So the pressure wave goes like this, and it gets returned from here, right? So if there is oil, what is going to happen is something like this. And if you have sensors here, or maybe you blast another thing, if you have, this is a simplified version, you have noise here, right? So this is another type of estimation. So this is the return from a return from this oil also, it's, remember, the geology, right? You have different layers. So there are return waves, scatterings, all sorts of stuff. So you can clearly see that what is coming back is a stochastic waveform here. From the oil, you get one stochastic waveform. Then the noise also is another type of stochastic waveform. And you may collect some observations here. So you get a vector here, and you get a vector, and this is your data, and you collect the data at a bunch of sensors here. And then you put, maybe you do the experiment multiple places so that if there is no oil, then what you are going to get is just the noise alone. So the you have another sensor which is just observing another. Remember, the whole thing being stochastic, this noise and this noise are not exactly the same. They may have the second order properties and first order properties the same. So you can't say I'm going to subtract this noise. So you can see how stupid that will be. You take these observations, subtract it from here, you are not going to get signal. That's the whole problem, right? Because this is a stochastic process, this is a stochastic process. This is one realization, this is another realization. So the question is, how do you use this all this data and try to estimate and see whether there is yes or no about. So what I was trying to say about the doctor's office is, suppose you have, you go to doctor, you have a heart, right? So the doctor listens to your heart. Remember, there are also, heart is murmuring and there are all sorts of stuff going on. So you get some noisy version of some data. So the doctor is going to listen to this data. Then you have heard the doctor would take the stethoscope and put it somewhere close by your heart and listen to that area. And then he or she will put the stethoscope back here. I mean, this is close to the heart. You're not going to put it on your head, but close to your heart. And so you collect this data. Then years of experience, they are able to cancel out this and figure out the whether the waveform that you are hearing is the normal heart or heart with solutions, etc. So this is called adaptive cancellation. So we'll talk about this problem also next week. So you can see you have right now you have a lot of tools to address different kinds of problems. So this is a big area. I already touched upon one set of things using this maximum likelihood principle. Now we will go into time series analysis. What is this? That is what this is. So the unknown is could be xn plus 1. If I know the past, give me the future. That's a simple problem. If I know the past, tell me what is going to happen tomorrow. I want to estimate this using these values. Linear or non-linear, we'll consider all this tomorrow, I mean next Thursday. So let me stop here. I think this is a good time. It's 14. So Hifeng,
yeah, I'm here.
You can send the questions to them. So I'm going to give you, I'm going to, Sushant, you too. I'm going to give you half an hour. You need to switch on your videos. I'm not, if somebody's video is not on, we are going to note the name. We are not going to ask you to switch it on. I'm not going to say this again. So please switch on your videos because I want to make sure no one does any hanky-panky. And I'm going to stop the recording. And Sushant, did you send it to them?
Yeah, yes, Professor.
And we'll give you half an hour, right?